Here are two more examples on deciding between SN1 and SN2. Here we have a secondary substrate, great leaving group. We have a poor nucleophile, and we have a protic solvent. And so protic and poor nucleophile, and also the possibility or the fact that it's secondary or tertiary, leads us to SN1. I'm going to move that out of the way. So secondary SN1 is probably going to be favored here, mostly because of the poor nucleophile and the protic solvent. So the first step here, of course, is loss of the leaving group. I want to use red arrows. And that gets us to this secondary cation. We formed a secondary cation. That's your clue to look for rearrangement possibilities. Can I make this a tertiary cation? In this case, I hope that you've said, yes indeed. There's a hydrogen right here. If I move it over, I can create a tertiary cation. So this hydrogen is attached to a tertiary carbon. If we do a rearrangement or a hydride shift, we can produce this tertiary cation. Now we have a more stable cation. It's ready to react with our poor nucleophile. And of course there are two lone pairs on water. We can use either of them. One arrow push for the nucleophilic attack. And we get to this compound. We're almost there. Don't forget that we should have a plus here on the oxygen. We've used one of the lone pairs on the O to create a third bond to O. We have not done anything to these hydrogens yet, so both of them should be here. If you forget to include both hydrogens, you're not going to get full credit for this problem. And the last step, of course, is to remove one of those hydrogens. So this is the sometimes useful proton transfer step. We don't have to memorize when we need this. We just observe by properly drawing arrows and properly drawing the intermediates. We observe that this intermediate needs a hydrogen removed. And we can use water, the solvent, just like we use it as a nucleophile, we can use it as a weak base. And we use that arrow push. And that gets us to this final structure. This is not a stereocenter right here. It has two ethyl groups attached, so I don't need to indicate that we've created two enantiomers. I just need to draw that. And so that is our final structure. And here we saw, again, because we used the poor nucleophile, which created an oxygen with a charge, we needed to remove one of those hydrogens at the end, and that was when we used our optional proton transfer step. Let's look at this, this one right here. We have a secondary substrate. We've got OH group, and we know that that is a poor leaving group. So we need to do something to that before we can actually proceed with whatever reaction we choose. We have no solvent indicated. And we have, in this case, HBr. If we treat that as sort of being a source of Br minus, we have a good nucleophile right there. So that's our nucleophile. We've got some HBr. The solvent won't help us decide, but the fact that we have a poor leaving group also leads us to an SN1 type of mechanism. And of course, if we draw this and say, hey, we just lost our leaving group, we've got a problem. We just created a very strong base. So we should never create OH minus. So I'm going to get rid of this. And let's try something else. So the poor leaving group needs to be turned into a good leaving group before we can do anything, and that, of course, is when our proton transfer step, being the first step, comes into play. I'm going to pretend there's a HBr bond here, and we're going to draw that arrow like that. So now I'm doing a proton transfer step here to turn our poor leaving group into an okay leaving group. So now I have this cation. Water is a decent leaving group, so now is the time to do our loss of leaving group step. That leaves us with a secondary cation, some water, and of course the Br is remaining here. So again, excuse me, secondary cation. Can this rearrange to form a more stable cation? And I hope that you conclude that right here is a hydrogen, and if it moves, we get a tertiary cation. So let's show that rearrangement. So now I have a tertiary cation. It's more stable than the secondary. It is ready to react with my nucleophile. Most likely the nucleophile will be the bromine, sometimes maybe the water, but of course if we use water we end up with an alcohol, and that doesn't really give us much progress towards a new product here. So let's assume that the bromine is going to be the best nucleophile here. We often don't, our goal is often to change the type of functional group that's present on the molecule. So if I were to just put an OH group here, that's not really going to be very productive. So let's leave it like this, and the byproduct is H2O. So we're getting this secondary bromide. Is this carbon a stereocenter? Well, it's on a ring. It's part of a ring with nothing else around that ring. So both sides, if you think about this side of the ring and this side of the ring, they're equivalent. And so that is not a stereocenter. We don't have to show any stereochemistry. We don't have to indicate that we produced both enantiomers in this case. But that's always a question that we want to ask ourselves when we're finishing up one of these problems.